All right, this is sequences and series. First, today we're just going to talk about sequences. Sequences are just a set of enumerated numbers that are in some order. We can start the series wherever we want. A sequence is said to converge if the limit is a constant. So for example, if my sequence went to this value c, that would be a convergent sequence. A sequence is said to diverge if either the sequence goes off to infinity or negative infinity, or it doesn't tend towards anything. Now we can still have a convergent series that alternates because I can have it going towards 0 or towards any other number. So it doesn't have to be completely increasing or decreasing or anything like that. When they denote sequences on the AP test, they're going to denote them with curly braces, and that's how you know that you're talking about a sequence and not a series. We can go through plugging in values to find the sequence. So if n is equal to 1, you're going to have 3 minus 1, or 2. If n is equal to 2, that'll leave you 3 plus 1, which is 4. N is equal to 3, you're going to go back to 3 minus 1, because this piece right here is alternating. So this would be 2, 4, 2. So does this sequence have a limit? It might have been harder for me to determine that here, but writing out a couple of terms, I can see that there is no limit. It's alternating between 2 and negative 2. So the sequence says limit does not exist, so the sequence is said to diverge. Same thing with number 2. We're going to go number by number. So if n is equal to 1, you're going to get 1 over negative 1. If n is equal to 2, you're going to get 2 over negative 3. 3, you would get 3 over negative 5. And keep going. So what is this tending to? Is it going to something? Now looking at these numbers, I think it's harder for me to see, but looking here, this is our sequence. The degrees are both 1, so the degrees are equal, so the limit is the ratio of the leading coefficients. So it's going to be 1, negative 1/2. Since that limit exists, this sequence is said to converge. The next one, same thing, plugging in 1, we'd have 1 over 1, 2 over 2 squared minus 1, 2 cubed, which is 8 minus 1, 2 to the 4th, which is 16 minus 1, 32 minus 1. Now I can definitely see my sequence is getting smaller and smaller and smaller, so I'm assuming this is going to go to 0. But looking at this, the degree at the top is 1, and we have an exponential on the bottom. So we could do L'Hopital's, because technically we do have infinity over infinity. But one thing we want to start doing is paying attention to growth rates. What grows faster? A polynomial of degree 1 or an exponential? So definitely an exponential is going to grow faster, so this is going to go to 0. But one L'Hopital's is going to take that and show that to you. So this sequence converges. So like I said, we got to pay attention to growth rates because it makes things so much faster. So n factorial is going to grow faster than an exponential. The bigger the base, the faster it's going to grow. Then the polynomials, the higher the power, the faster it'll grow. And this right here is sometimes hard for people to understand why that's true. So if I say n is greater than natural log of n, so I'm just going to exponentiate both sides. So that would tell us that e to the n grows faster than e natural log of n, which is n. And I think that's clear to everybody. We all know that that would grow much faster. So natural log goes to infinity. It just grows at a very, very slow rate. So there are two different types of formulas for sequences. There's the explicit ones, and that's where you're using the term number. So if I want to know the fifth term, I would plug in n equals 5. It's easy to generate any term you want because the formula is in terms of the term number. The harder ones to deal with sometimes are the recursive. Those use the previous values. So if I want to find the next term, I would have to generate every single one in front of them. I think the most famous one everybody knows is Fibonacci. So it starts with 1, 1. You add them and you get 2. Then 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And so on and so forth. So if I want the 10th number, I'm going to have to generate all the previous ones. The other thing with recursive formulas, you have to have seeds or starting points, some initial condition for them to grow off. I can't tell you to add 2 terms to get to the next term unless I tell you what terms to start with. And again, that's the Fibonacci. And again, there's lots of ways we can write this. We could have said, I'm going to find the nth term, and I'm adding the n minus 1 and the n minus 2 terms. And again, here's my seed. Or I could have said, I'm going to find the n plus 1 term. Then the 2 previous terms would be called n and n minus 1. So there's lots of ways to write the same formulas. All right, an is equal to an minus 1. Notice it is recursive because it's dealing with a previous term. They gave me a starting point. So this right here is a1. So if I want to find a2, it's going to be 2 times a1 minus 1. So 2 times 4 is 8, minus 1 is 7. And then we do it again. 2 times 7 is 14, minus 1 is 13. 2 times 13 is 26, minus 1 is 25. And so on and so forth. So as we can see, this sequence is getting bigger and bigger and bigger. It's going off to infinity. It's diverging. So the sequence diverges. One thing that is kind of important to do, and we don't do it a lot of it, but you will need to do kind of patterns later on in the chapter. So sometimes we want to create the formula ourselves and know what it is. So looking at this first one, it's a series that we've already seen before. We've already seen these type of series. This is called arithmetic. To get to one term to the other, you add 4. So what I think of is to find the next term, or to find an, I'm going to do the starting point, which is 3. And then I'm paying attention to the slope. To go from one digit to the next digit, it's 4n. So looking at that, if n is equal to 0, we do get the first term. If n is equal to 1, I can get the second term, and so on and so forth. Now, if I always wanted to start at 1, I could still do that. It's just going to be a little bit, tiny bit more work for me. So I know that an is going to go up like 4 to the n. If I plug in n equals 1, I want to get 3. So if I plug in n equals 1 here, I get 4, but I want 3, so I'm going to subtract 1. So let's see if it works for all of them. So if n is equal to 1, we do in fact get 3. If n is equal to 2, we do get 7. And how you create the patterns is not important because it doesn't really matter if you start at 0, if you start at 1 for most of the problems. What really is important is where it's going to. And the formulas are all equal. So 4n plus 3 and 4n minus 1 are growing at the same rate. They're just one term off from each other. Okay, so looking at the next one. On the top, we have 3, 4, 5, 6, 1. I think this is probably 7, but it probably was reduced. Again, that's arithmetic. What is the slope of that? What is each term going up by? It's going up by 1n, and then I could put the starting point. So if n is equal to 0, I would get 3. If n is equal to 1, I would get 2. So n plus 3, and on the bottom, how is that changing? Well, it looks like it's going up by 3. So I can say 3n plus 2. And again, that's with n starting at 0. If we start at 1, we could do something else. Okay, so now sometimes the sequences get a little bit harder. So what's important is focusing on different changes that are happening. So what I see this one right here, I have this 1 in each one. So 1 plus something. Now the next thing I'm going to look at is just the numerators. So let's see what's happening on the top. I've got 1, then 3, then 7, then 15. It's not geometric. I'm not multiplying by the same thing. I'm not adding the same thing. So I'm not exactly sure where that's coming from. So the next thing I sometimes try to do is put the term numbers down. I could call this let's see, this one would be the first term. This one would be the second term. This one would be the third term. This is the fourth term. Do you see a relationship between the term number and the value? Well, it looks like it's the term number squared minus 1. So this would be n squared minus 1. And look at the bottom. The bottom numbers are going 2, 4, 8, 16. And in fact, that is n squared. And does that make sense? The top is exactly 1 less than the bottom, so it would be n squared minus 1. 8. 0, 3, 8, 15, 24. Okay, so it doesn't look arithmetic. It's not geometric. If I put my term numbers down here, I'm not sure if I see a pattern. Oh wait, I think we do. Isn't it n squared minus 1 if we start with n equals 1? Now I understand sometimes this is very hard to see. So one thing that you guys know about is common differences. So, I don't know why it's not erasing. Oh, there we go. So if I look at the first common differences, I get 3 here, 5, 7, 9. That's the first common difference. So if I look at the second common difference, I shouldn't say common difference, I should say difference, the second difference. So the first one's not a common difference, it's the difference of each one. Now since the second difference is constant, we know it's coming from n squared. So it has something to do with n squared. So that can help. If it's the third difference that finally gets to be common, then it's going to have something to do with n cubed. Determine if the sequence converges or diverges. If it converges, find the limit. Now remember what it means for a convergent series. That means the limit exists and is finite. Diverges means the limit does not exist, it's infinity, or it doesn't exist at all, it's alternating or something like that. So 1 plus negative 1 to the n. Not a limit that we're normally used to, so I'm going to go ahead and write out a couple terms. So I'm going to start with n is equal to 1. If n is equal to 1, I'm going to get 0. If n is equal to 2, we get 2. If n is equal to 3, we get 0. So I think this limit does not exist, which means the sequence diverges. This is one we're used to seeing more of. You see here that the degrees are equal. So as we go to infinity, it's going to be the ratio of the leading coefficients. This limit is a constant and it's finite, so this sequence is said to converge. That's a sequence. 11, the degree of the top is 2, the degree of the bottom is 3, so the bottom's growing faster, which means this limit is 0, which means the sequence converges. Now we've already seen this one on the top. It went 0, 2, 0, 2, but what's happening to the bottom? The bottom's getting bigger and bigger and bigger, but the top is alternating between 0 and 2. Overall, it's going to continue to get smaller, and it's going to go to 0, and this converges. Now, one thing that comes up a lot in Taylor polynomials in this chapter is factorials, and that's one thing that you haven't used a lot. So just remember 5 factorial would be 5 times 4 times 3 times 2 times 1. So when we have factorials, sometimes we'll decrease the first one down until we see the bigger one down until we see the smaller one. So I know n factorial is bigger than n minus 2 factorial because our n's are always positive. So that means I'm going to take the bottom one and I'm going to decrease it. So n factorial is the same thing as n times n minus 1 times n minus 2 factorial. That's where you stop. I know to stop there because that's what's on top. So these guys cancel. So e to the n is the same thing as this. The degree of the top is less than the degree of the bottom, so it goes to 0, which means this converges. And the last one is a limit that they actually don't put on the AP test, but it's one that you should know. It is an improper limit. It's not a L'Hopital's improper, it's a different one. It is 1 to the infinity. So that's improper because it's conflicting. As if I approach 1 from the right, like something like 1.001, that's going to get bigger and bigger and bigger and go off to infinity. But if I take something smaller than 1 on the inside, let's say 0.999, as we go to infinity, that's going to get smaller and smaller and smaller. So when it's improper, you have to do the natural log of both sides to get rid of that power and kind of simplify things. So y is the same thing as with this. I'm going to find the limit. Sorry, I didn't write the limit. And I need to do this because it's improper. The problem is with the power. The power doesn't help us. It's giving, so we're going to take the natural log of both sides because that's one way we get rid of powers. When we can take the natural log, we can bring powers out in front. So one thing we can do is pass this natural log through the limit because it doesn't have anything to do with n. So now we have the natural log of y is equal to the limit as n goes to infinity of the natural log of this thing. Now the whole reason we'd want to take the natural log is because it gets rid of powers. We have a nice property. The property is that the powers can come in front. So now we have the natural log of y is equal to the limit as n goes to infinity of n times the natural log of 1 plus 1 over n. Now the issue comes from as I go to infinity. You're going to have infinity right here. And this is going to leave you with a natural log of 1, which is 0. And 0 times infinity is also improper. Think about it. Everything multiplied by 0 is 0. Everything multiplied by infinity is infinity. So what is 0 times infinity? So we have to get rid of this. So what I want to do is try to make it into 0 over 0 or infinity over infinity. So I'm going to change this multiplication to a division. They're mathematically equal. Multiplying by n is the same thing as dividing by 1 over n. But how this helps us out is now we're going to have 0 over 0, which is our traditional L'Hopital's. So going over here, just running out of room, natural log of y, we're going to do the L'Hopital's. I always like to put an L. That just is my way of knowing that I did that. So that means you can take the derivative of the top and the derivative of the bottom. Remember, if it's on the AP test, you have to justify it. You have to say that the limit of the top is 0, the limit of the bottom is 0, so therefore you can apply L'Hopital's. So the derivative of the natural log is 1 over 1 plus 1 over n. Chain rule, the derivative of 1 over n. Remember, you're doing the derivative of 1 over n. It's going to be negative 1 over n squared. And we take the derivative of the bottom. That is also 1 over n, so negative 1 over n squared. These guys cancel. So as we send n to infinity, this is going to 1. So we have the natural log of 1, which is equal to y. So exponentiate both sides, so y is equal to e. So this, in fact, goes to e, and it converges.